Hi everybody. So in today's video, I'm going to be performing a simulation using Geometric Brownian Motion, but the point of this video is not to actually get the simulated prices, it's to see how long it takes to compute the price. So I'm going to be using Geometric Brownian Motion on Python and in C. So the stock that I'm going to be examining is NVIDIA, and I've loaded their close prices over here from Financial Modeling Prep. So the thing about Financial Modeling Prep, they changed their API structure. So every video you saw me using that historical data endpoint from Financial Modeling Prep, it does not work anymore. The alternative for a free subscription is just the historical price end of day, and yeah, that is restricted to a set number of stocks. Like the previous one, like all the previous FMP APIs that I use, you can put any ticker on it, but now you can only have a select few tickers that you can fetch, and then the rest like just don't allow you to pull. But yeah, I guess just let's get right to it. So I have close over here, so let me come here and do ROR equals close of 1 divided by close -1. And I will take the log return, so I'll do numpy.log. So now for the geometric Brownian motion model, we need the stock price, the drift, the volatility, and the time. I'm going to set time equal to 1.0 divided by 252 trading days. So I just want to examine one trading day. So drift is going to equal numpy.mean of ROR, and then volatility is going to be numpy.standard deviation of ROR. So I have all the parameters, so let me get rid of this. I'm going to, well actually, I need a set number of steps equal to, I'll start them off at, let me think, I need to measure them. So yeah, okay. I will do steps as numpy.linspace of 1 to, what do I want the max step to be? Oh wait, what am I doing? I should do 100 to 10,000. And then let me also write, so n is going to equal 50. So I'll put n as the differential here. So we have steps. And then paths is going to be numpy.linspace of 50 to 500, or rather I'll do 50 to 1000, comma n. So I'm trying to think like what kind of plots do I want with this. If we have paths and steps as different combinations, I think this could serve as a good 3D chart. So yeah, let me go ahead and import. Wait, what's going on? Oh, my caps lock is on. Import matplotlib.pyplot as plt from mpl toolkits.mplot3d import axes 3d. So now I can do x and y equals numpy.meshGrid of steps, no, paths and steps, and then z is going to be numpy.zeros of n by n. Okay, so now that I have that, they can be inputted. So I guess if I come up here and define PyGBM, S, drift, volatility, time, steps, and paths, Okay, so actually I have to make an important, I need to look into this, so I'll do pi GBM of S. Let me go ahead and define S. So S equals close, the last element of close. So then S drift, volatility, time, steps is gonna, so steps is gonna be y of 0, 0, and then paths is gonna be x of 0, 0, just to keep things simple. So what I need to do now is do dwt equals numpy dot random normal of steps. So I need to print the bounds. So numpy dot min dwt and numpy dot maximum of dwt. And actually, let me just go ahead and put this as 200 just so I can get like an accurate range because I'm going to need it for the C portion. So run it. Negative 3.5 to 3.2. Okay. Now I know the bounds for the Monte Carlo. Let me try 2000. Let's just see if the bounds hold. 3. I'll do negative 3 to 3. Yeah, I'll do negative 3 to 3. So let me come back here and do steps. So this is going to be total equals 0 for I in range. Oh, wait, I need dt as well. So dt equals t divided by steps. So for I in range paths, I'll define S0 equals the initial stock price. And then for J in range steps, this will be S0 plus equals drift times S0 times delta time plus volatility times S0 times dwt of J. So then over here I'll do total plus equals S0. And then down here I will return total divided by paths. Okay, so I'm going to come down here and do pi result, and then I'm going to print these out. So print pi result. So run it. NumPy float cannot be replaced by integer. Okay, I'll just do this. Steps equals the integer of steps. Paths equals the integer of paths. So now let me run this. Okay, so that's the simulated price that I got for it. Again, I'm not really worried about the results right now. I'm just trying to code like the speed test. So that's pi GBM. So I'll come here and define C GBM, S drift, vol time, steps, and paths. So right now I'll write pass on this, but I'm gonna wait. Why did I do that? Okay, so I'm gonna open up a new file, and I'm gonna call this vr.c. So this is gonna include stdlib.h, include math.h, include time.h. So this is going to be double back test. Simulation. So this is going to take the argument of stock price, take the argument of drift, take the argument of volatility, take the argument of time, and then the integer of steps, and the integer of paths. So let me just double check the same inputs as drift, vol, t, step, paths, as drift, vol, t, step, paths. Okay, good. So I'll define total equals 0.0, and then I will do double dt equals t divided by cast double steps, and then for int I equals 0, I is less than paths, plus I. So let me go back and check. Okay, all good to go. Oh, right, before I even do anything with that, let me do double dwt is going to be integer of num equals 35, and then double dw equals random mod 2 times num plus 1 minus num, and I'm going to return dw divided by 10.0. So that'll be the bounds. So I'll come over here and do double s0 equals s, and then for int j equals 0, j is less than steps plus j. So this will be s0 plus equals drift times s0 times dt plus volatility times s0 times dwt. And then over here, I will do total plus equals s0, and then return total divided by cast double of paths. So that part is done. Yeah, total divided by paths. So I'm going to come over here and import C types. And then inside here, I'll just create the function. So it'll be, I'll call it quant. Oh wait, let me go ahead and actually compile the C code. So I have vr.c. I think my code is correct. So I will come over here and do gcc minus shared object of vr.so, vr.c, fpic. Okay, so then, yep, we got vr.so. So I'll call this quant equals c types dot cdll dot slash vr.so, and then it's going to be quant dot simulate. Oh, is out. Simulation dot arg types equals. So this is going to be c types dot c double, and actually I can see these right here. So that's 1, 2, 3, 4, and then c types dot c integer and c types dot c integer. So then it'll be quant dot simulation dot res type equals c types of c double. Yeah, c types of c double. So now I will do so steps equals the integer of steps, paths equals the integer of paths. So then it'll just be, let's see, I guess I could just do result equals quant.simulation of s, drift, volatility, time, steps, and paths, and then return result. So now I'm going to come over here and do, I'm going to copy this, paste it here, but then I'm going to change this from pi result to c result and cgbm, and then print them alongside. So print pi result and c result. So clear that. Yeah, clear. Python 3 vr.py. Okay, not too Oh, the C code is frozen on the random number generator, so I have math and time. Yeah, that was what I forgot to do. So I have to do srand time null. So that way it'll be a completely different stochastic process. So let me just load up. Yeah, this is where I compiled it. So clear Python 3 vr.py. Yep, they're pretty much about neck and neck, some variation, but they're simulating. So what I can do now is, so I will call this z pi, and then I'll come over here and do z c equals numpy dot zeros n n. So I'm going to come over here, tab it twice, and do for I in range n, and then for j in range n. So this is going to be y of I of j, and then x of I of j. So paths and steps I, j, I, j, and then just so we can see what's going on, I'll do print I and j. So now, oh, wait a minute. Oh shit. Oh no. I completely forgot. I just have to import time, and I have to create a decorator. So I will do def time it takes a function argument, def handle gets the arguments and the parameters. So this will end up being z equals f a b. Oh wait, no, before that I should do t0 equals int of time dot time. And then over here it's going to be t1 equals the integer of time dot time. And I'll call this dt. I'll call it ds equals t1 minus t0, and then return ds, and then return handle. Okay, so I don't actually need to return the option price anymore. I just need to decorate the function, so this will be time it. And I know it's crazy seeing a C function using a decorator, but this is going to be at time it, or at least Python style. But okay, so I've got the two in there. So pi result and C result are going to be times right now. So I will do z pi of ij equals pi result. And this is going to be z of c of ij equals c result. And then now I have the 3D plots, so I'm going to come over here and do fig equals plt.figure, ax equals fig.add subplot 1 to 1, projection equals 3D, and then ay is going to be fig.add subplot 1 to 2. Projection is going to equal 3D. So then I will come over here and do AX, or maybe I'll do it like this. Actually, yeah. AX dot set title of seconds model ran, and this is going to be Python, and AY dot set title of seconds model ran, and it's going to be C. AX dot set X label is just going to be, let's see, paths and steps. So X label is going to be paths, and then AX dot set Y label is going to be steps, and the same thing for AY. Yeah, AY. So then it'll end up being AX dot, so I'll call this the Python equals AX dot plot surface X, Y, Z, pi, C map equals jet reversed, and the C equals AY dot plot surface of X, Y, Z of C, C map equals jet R, and then I'll do fig dot color bar of the Python, and then AX equals AX, and then fig dot color bar of the C, AX equals AY, and then PLT dot show. So let's check this out. So I will do Python 3 vr.py. Okay, this might take some time, but hey, I'm here to wait. Um, yeah, option pricing has always like really interested me. And there was actually a point in my life where I kind of wanted to like just do some research and develop like a new options pricing model. Like I was told like the best option pricing model is the one that could fit like the best volatility smile to the implied volatility curve. So it's like there's a hunt for options models like that. Um, this is taking a long time. It's going to take longer because I set it to 50. So maybe what I should do is take this away, like stop the simulation right there because it's going to run for a long time. Instead of 50, I will do 10. Yeah, let's do 10. So clear that, run it. Okay, I can see. Yeah, this is gonna do better. Yeah, it's getting juicier. I hope there's no errors in the plot. Like I kind of just like steamrolled through that, but I think it'll load out good. And the color bars like show like what those color maps mean in terms of like numerically. Like for example, with jet, it's like the more dark blue it is, the more positive it is. The more dark red it is, the more negative it is. Well, at least in the reverse version, it's reversed in the other one. But yeah, AXAY. Yeah, I was gonna be like, yo, if I have a fucking error in this, I'm not gonna be happy. Second model ran Python, second model ran C. Okay, it's getting very hectic up here. Okay, it's almost done. What does it even go up to? 100 steps to 10,000 steps. Okay, that's probably why it's taking long, but we're almost there. We're almost there. Oh, I completely forgot this is even for a stock. I was like, wait, NVIDIA. Oh, so we're computing NVIDIA's option pricing times. Okay, so this looks very good. So it's saying so we could see that with all the simulations, Python took 4.5 seconds to compute at the maximum. Well, it actually says 6 seconds, while C ran the model within half a second. There were some points where it was over, but yeah. I mean, clearly we know we know which model is faster. So C wins in Python. But yeah, I thank you all for watching this video. I'm gonna keep coming out with more and more good quant content. So stay tuned. Peace out.